Hello guys, welcome to my second video regarding the MATLAB implementation of the Kalman filter. In this example is a little different from the Ninja and the Pigeon. Basically, in this example, I have a cannon on top of a building, and that cannon will launch a cannonball and then a feather, and we will see what the differences are in the Kalman filter and in the results that we get. Okay, so as I done before, I will first show you the examples in the graphic examples, and then try to explain a little bit of the code. So the first thing I will show you is the cannonball example, followed by the feather example. As you can see, the only difference between the cannonball and the feather is the noise that the object suffers. Okay, the noise in the measurement will be the same, the position will be the same, the initial velocity and acceleration will be the same. Okay, there is also another thing that changes, that is the covariance in the measurement, because we have to adapt our covariances regarding the noise that we got in the model. So the first thing that I want to show you is, like I said, the cannonball. We theoretically know what the cannonball behavior will be. So as you can see, we got the building over here and the cannon, and we will launch a cannonball. This graphic represents the X position at a given time. This one represents the Y position at a given time, and this graphic represents the real position. So the green dots is what the ninja sees, or what a person sees, okay? And these red dots represents the path that the cannonball is doing. As we've seen before, the cannonball has a little noise, so the behavior is almost perfect. So in this case, we have the need to trust in this model way more than we have to trust in the measurements. So let's see the output that we get. As we can see, the output is very accurate. We got a maximum error in Y of 3%, and the maximum error in X is 1%. So if we get closer, and you see that the cannonball is dropping for 500 meters high, okay, and is getting almost 250 meters distance from the beginning of the launch. Okay, so if we see this a little closer, we can see that there is an error of 3 meters more or less in X. This distance between here and here is more or less 3 meters, as we can see here, and we got a distance of almost 13 meters in Y. Okay, these are very good results as far as I'm concerned, especially if you look at the measurements that we get. Okay, those are very good results. The reason that we get this much of good results, it's because we are trusting way more in the model than we are trusting in the measurements. Okay, so now it's time to see the feather. So we just need to change this over here, Control R, okay, and then we clean this over here. As I said before, the only difference is in the noise of the object. In this case 0.05, and in this case 25. Okay, and also the covariance matrix of the measurements is also different. Okay, so let's run this example and see what we get. So we got the building over here, we got the cannon, and let's drop the feather, or launch the feather, better saying. So as you can see, the Y the Y position of the feather is accurate with the model. That means, however, the X position, it is not. The reason for this is that I only applied the noise error in the X position because the feather is falling, so there is nothing, or there should be nothing in this model at least, that is affecting the falling of the feather. However, the wind on this day will affect the velocity and the position of the arrow. Okay, so as we can see, the arrow moved almost dropped like a rock. Almost looks like it was dropped instead of launched. So let's see what we get for the results. Remember that these green dots is what we think where the feather is. It is they are very far away from the feather, and these blue dots will represent the Kalman filter observation. Okay, so there is a funny thing here, and I'm glad that this happened. If you have seen the videos before, you know that or if I don't know if they are in the videos, but if you look up this in the internet, you will know that the Kalman filter needs time to stabilize. Okay, so we see that there is an error of 0% in the Y position because we are trusting very much in the model. Okay, so the error is 0%, and however we got an error of 300% in the X position. Okay, this error is the maximum error that was ever happening at a given time. What I mean by this is that, for instance, it was probably in the 3 or 4 seconds. This distance is great. It's a great distance from here. I don't know how much, but I can check it out for you if you guys would like. 10, 20. We see that in the 3 seconds after the launch, we got an error in between the Kalman fight and the real position of almost or over 20 meters. Okay, that's a great error. However, what happens is that as we move along the line, we can see that the Kalman filter is approaching the real position of the feather. Let's try. Yeah, let's try. For the very first time, I will try this with you. If we put 100 seconds in here, this isn't over yet, but we can start to see that the initial error of the Kalman filter is a great error. Okay, but as it goes on in time, it will begin to stabilize. Okay, the reason for this is that in the beginning, as we have so little measurements, we are trusting way too much in the model, in the perfect model of the feather. And the tendency of the Kalman filter is to go in a linear line. Okay. However, as time goes by and we start to getting more and more measurements, the Kalman filter will start to trust more on the measurements and start to converge to the line. Okay. As we can see, we got a 57% error. It's not as much as I was expecting. But the funny part is that if we go here, we can see that the real X, the real distance in meters from the error is in X, of course. It's 5. It's less than 15. Okay, it's less than 15 meters in error, and assuming that we are and at a given time the feather was in the X position of 100 or almost 100, I think that this is a good result. Okay, and I will show you why we got this results. I will put back the 10%, the 10 seconds. Okay, I will show you this example again. This is way faster now. Okay. We can see that in X the Kalman filter is converging. If we have more time, it would converge more. Okay, but now we will change the covariances matrix. This will affect how much we trust the model in X, and this will affect how much we trust the model in Y. Okay, so now in X, let's assume that we trust the model much. We trust too much in the model. What we will get is this. As you can see, this is the feather movement, and at the blue line is the basically that theoretical path that the feather should take. Okay, so basically, in order for us to get good results with the Kalman filter, we have to know the model, we have to know the measurements, and we have to play a little bit with the covariances in order for us to get a more approximated result of what we want. Okay. So now I will try to explain a little bit the coding that there is behind this. It is basically the same that was in the previous example, but now in 2D dimension. Okay. So basically the code is like we've done before. We define the duration, we define the matrices, we define the noise and the given the initial position and the initial velocity of the as we can see here, we define the initial position and velocity of the feather. We calculate the covariance matrix in X, and we got here in the measurement the covariances in the covariance matrix in the measurements. Okay, and then this is for plotting the building and the cannon. Okay, and then we basically do the path of the feather or of the cannonball. As we can see here, we are being influenced by the value that we give here. Okay, and we plot it. This is the plot. Okay, and then the Kalman filter calculation. Again, the first estimative of the position, the first estimate, the estimative of the covariances matrix. Okay, the gain, so on, the plot. Okay, basically we are doing kind of the same thing, but now in a 2D world. Okay, I will actually I got a break here. The only difference from this is I can see in a 3D world I can see in a 3D world the path of the feather and the Kalman filter that I was expecting. Okay, but I will give you this code. It will be on my blog, and I hope you guys understood what I said. I may have been a little confused, but if you got any doubts, you can ask me. Okay, thank you guys for watching, and I'll see you next time.